Hello everybody, welcome back to Hawk Tutor. Per special request today, we're going to be going over resonance structures in chemistry, which is a little bit different than my traditional math that you'll see on the channel, but we're going to be doing some chem right now. So let's get straight into it. First things first, we're going to start off with one example of resonance structure. So that is very poorly written. We're going to start off with NO3. So NO3 minus. So basically, just to quickly define what a resonance structure is, so it's going to go along with your Lewis dot structure, which is just the sharing of electrons throughout a polyatomic structure. And basically, it's just going to be a different way to configure those electrons within your Lewis dot structure. So it's basically just a series of configurations. And then at the end, you can create a resonance hybrid, which I will also make a distinction of towards the end. But first things first, we're just going to get the three resonance structures going for this polyatomic ion right here. So let me rewrite that up in the top corner, and then we can get started on how we're going to do this. So basically, first things first, what you're going to want to do is just see how many valence electrons you're working with. So I'm going to put VE up, so that stands for valence electrons. And we're going to get a value going for this. So N has 5 valence electrons. And for this, you can just look at your periodic table. It's going to be right there. It's whatever that group number is labeled. So N is going to have 5 valence electrons, and oxygen is going to have 6 each. So we're going to do plus 18, or 6 times 3. And then we're going to add 1 because it's NO3 minus. Sorry, I forgot to put that minus right there. But that is essentially all it's going to be. So from this, we know we're going to have 19 plus 5. That is going to be 24 valence electrons. So we're going to just note that right under NO3 here, 24 valence electrons. So we know we have 24. I'm just going to erase that real quick. That is kind of big. So now we'll get to work, right? So your central atom is basically going to be the one that is pretty much just starting right here. Usually it's going to be your less electronegative. Let's re-put 24 right there. Usually it's going to be your less electronegative atom that's in the polyatomic structure. But in this case, a very easy way to tell is through the fact that there's 3 oxygens. So you know that those are going to be surrounding your nitrogen. But in this case, nitrogen is also the less electronegative value. So that just goes to show you can use either of those to kind of figure out what your central atom is going to be. But obviously now that we know it's nitrogen, let's get to work. So we're going to have nitrogen right in the middle right there. And then oxygen is in the 16th group. So essentially it likes to double bond a lot of the time. Usually your halogens, or basically which is just the group before your noble gases in group 18. So the group 17 halogens will only do single bonds. But regarding oxygen, or really any other group below that, usually it's going to want to do double bonds, triple bonds, and everything is pretty much in question. But for oxygen and group 16 elements, usually they're going to want a double bond. But in this case, you're going to have 1 double bond and then 2 single bonds branching off for our first structure here. And basically for your central atom, with nitrogen, other than a few exceptions, which are include beryllium, boron, and I believe lithium, you're going to want to have 8 electrons per central atom. So we can see here that double bond's worth 4, and then these are 2 valence electrons right there. So we know that we did that correctly because nitrogen has 8 electrons binding to it right now. So now we have our 24. We know that we already have 8 being used for these connections right here, these bonding pairs. So now we're going to get our lone pairs going. So we already have 8. We can do 9, 10, 11, 12, 13, 14, 15, 16. Oop, my mistake. Let's retrack a little bit. That's a common mistake that usually gets made. With each atom in the polyatomic structure as well, those are also only going to have 8. So if it's double bonding here, this oxygen can only have 2 lone pairs. So you're going to have 2 lone pairs there. So we have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we've reached 24. Those are our valence electrons. So yeah, this is going to be our first resonance structure. So all we're going to want to do here is, because it's a ion, we want to bracket that in and then put our negative charge right here. And it's always good to label this as 1. So that's going to be our first structure. And just for space sake, I'm going to erase this, but you can take a screenshot, take a mental note, whatever it may be, of that structure right there. And then literally all you're going to want to do for the rest of the resonance structures are replace where that double bond is going to be for NO3 minus. So now the double bond went from here to over here. So the double bond changed location, and that is going to be a different resonance structure. And we just add the same amount of electrons around each atom. And perfect. So that's going to be our second resonance structure. So we can label this as 2, and obviously don't forget that minus right there. That is our second resonance structure, right? And now I'm going to erase that once again for space sake. And then our last one is simply going to be exactly what you may expect right over here. So that double bond's going to be right there. And then same amount of valence electrons going around each atom. And great. This is going to be our third structure right here. So that's our third resonance structure, and that minus always has to be there. And now I'm going to teach another concept that pretty much always directly links to this, which is going to be called a resonance hybrid. So I am probably not going to completely write this out, but resonance hybrid. So we have our resonance hybrid, and for NO3 minus, and which this also applies to a lot of different ions such as SO4 minus, PO3 minus, a lot of those different polyatomic ions this is going to be applicable for. And all it's going to be is this. So we know that the oxygen atom changed place within its placement around this central atom. So all you're going to want to do to kind of just signify that is go like this. So obviously we have our oxygen surrounding it via the bonds. So we know that these oxygens are going to be here in one of our resonance structures. And all we're going to want to do for our resonance hybrid is draw a dotted line between each of these. So we're going to have a dotted line right here, and then obviously we're not going to forget our minus. So this is going to be our resonance hybrid. You basically just draw one solid line, one dotted line between each atom that's connecting off of the central atom. And I've mentioned this a lot of times by now, but it's applicable for pretty much every polyatomic ion. Of course, there's going to be exceptions, as there is with a lot of things, but in general, it's a good rule of thumb for polyatomic ions to generally draw your resonance hybrids like this. But it's basically just going to be the general structure that it follows. So that's going to be pretty much it for resonance structures and resonance hybrids, but any questions, as usual, leave them down in the comments. And thank you for the request, my special guest that wanted this concept done, and I'll see everybody later. Thanks for watching to the end, and I'll see you guys in the future.